Alright, the next thing we're going to discuss are colligative properties. These are properties that depend on the concentration of the solute particles, but not what those particles are. In essence, we've learned how to make a solution by dissolving solutes into solvents, and now we're going to talk about what properties arise when we do that. The properties of a solution will be different from that of a pure solution, or a pure substance, I should say. So for example, water we know boils at 100 degrees Celsius, but salt water does not boil at 100 degrees Celsius. So the act of adding salt to water actually changes one of the behaviors of water. So the first behavior we're going to talk about is vapor pressure. So we need to know what that is again. It's the pressure of the gas that collects above the liquid in a closed container. Remember, right at the surface of a liquid, molecules are evaporating and becoming a gas. And some of those gas molecules that are above it are going back down and becoming a liquid. There's an equilibrium situation that's set up here. So if we call a substance volatile, what we're really saying is that it becomes a gas very easily. So there's lots of molecules that are leaving the surface of the liquid and becoming a gas. Acetone, gasoline are examples of these. Anything that as soon as you open the container you can smell what it is. The reason you're smelling it is because it is already turning into a gas and reaching your nose. A non-volatile substance is one that has a tendency to not become a gas, or it resists becoming a gas. Water is a good example of a non-volatile substance. Okay, so let's talk about the very first colligative property. It's going to be vapor pressure lowering. Okay, so when we create a solution, it is going to lower the vapor pressure versus the pure substance. Okay, so the reason that the vapor pressure is lowered is because there are solutes taking up some of that top layer of liquid. Let me draw this out for you. Alright, we have a container here, and in this container we're going to put some liquid, and I'm going to represent these molecules with X's. So let's say that this is water. Okay, and every X represents one H2O molecule. Okay, so right now we have a pure substance, and I'm just going to fill in the rest with water. Alright, now let's say that I start adding some salt molecules into this liquid here. Okay, so when I do that, those salt molecules are going to dissolve and spread out in my container of water. So they're going to effectively sit in between those X's. So I'm going to do an X, that's water, and then I'm going to do an O here, and that'll be an NaCl molecule, or maybe it'll be an Na ion, and something else would be like a chlorine anion, because that's going to dissolve. Okay, so we are fitting these things in between the water molecules. That means there's not as much water at the surface as there was before. So we know that the sodium ion and the chlorine ion are not going to vaporize and become a gas, but the water molecules could. So that can come up and become a gas, and so can that one, and so can that one. That means right now, at the surface of the liquid, we only have 3 molecules of water that are able to vaporize and become a gas. Whereas over here in the pure substance, we had a lot more than 3. That means that the vapor pressure over here is going to be a lot higher because we're making more molecules of vapor. Over here, the vapor pressure is going to be lowered because we have a lot less molecules of water that can become a vapor or a gas. So as we said right here, less solvent particles are able to reach the surface with enough energy to escape the cohesive forces of the solution and evaporate. That means equilibrium is reached faster and the vapor pressure is decreased. Okay, now that we've talked about vapor pressure lowering, let's talk about Raoult's law. Raoult's law says that the vapor pressure of the solvent above a solution is equal to the product of the mole fraction of the solvent and the vapor pressure of the pure solvent. So we've got a few variables here. P stands for the vapor pressure above a solution, and P naught, that's how we say it when it's got this little degree symbol, that means P naught, is the original vapor pressure of the pure solvent. Okay, so down here we have the vapor pressure above a solution, we have the mole fraction of the solvent times the vapor pressure of the solvent. Remember, we talked about mole fraction back when we did gas laws, so we're just reviewing a little bit. Remember, the mole fraction of a substance is the number of moles of that substance divided by the total number of moles in the solution. Okay, so let's do a practice question. If 0.34 moles of a non-volatile non-electrolyte are dissolved in 3 moles of water, what is the vapor pressure of the resulting solution at 25 degrees Celsius? Okay, so the first thing we need to do is write Raoult's law. Alright, so we have the vapor pressure above the solution, the mole fraction of the solvent, and the vapor pressure of the solvent. Now, it's important that they tell us this is a non-volatile non-electrolyte. When they say non-volatile, remember that means that it does not easily become a gas. There are some problems where they would give us a volatile electrolyte, and in that case it is going to contribute to the vapor pressure over the solution. Some of the vapor will be from the solvent and some of the vapor would be from the solute. Now in this case, since we have a non-volatile solute, that means that all of the vapor pressure above the solution is going to be due to the solvent. In this case, water is the solvent. So we're only going to plug in information about water. So we need water's mole fraction and we need the vapor pressure of water at this temperature. Now we know how to do the mole fraction. We're going to do the moles of water over moles of everything. And then the vapor pressure of water at 25 degrees Celsius is 23.8 torr. Now it doesn't really matter what unit of pressure you decide to use. It's just whatever you pick over here is going to be the same unit over here. So since our table gives us torr, that means our final answer is going to come out in torr as well. Alright, let's get the mole fraction for water. Okay, so we've got 3 moles of water over the total amount of moles in the solution, and here's what we come up with. Remember, mole fraction is a unitless number because moles on top cancels moles on bottom. Now we've got our pressure of the water at 25 degrees Celsius is 23.8 torr. I think we're ready to plug into Raoult's law. And we come up with 21.4 torr as the vapor pressure above our solution. So here's the mole fraction, here is our vapor pressure of water at 25 degrees Celsius, and we need 3 significant digits in our answer because we have 3 sig figs up here in the problem. The 25 degrees doesn't count because it was pointing us towards a vapor pressure. Okay, remember the normal or standard boiling point is the temperature at which the vapor pressure of a liquid is equal to the standard pressure. That's the 1 atmosphere is the standard pressure. And remember STP, that's where we get our standard temperature and standard pressure from. So the normal boiling point is whatever temperature it is when the vapor pressure is equal to 1 atmosphere. Alright, with that in mind, let's look at the second colligative property. We have boiling point elevation, meaning it's going to go up. Okay, a couple of things about this one. This occurs when the solute that you add is non-volatile. Okay, that means it's not going to readily produce its own vapor. The next thing is that we're going to have to increase the temperature in order to get the vapor pressure up to this standard pressure of 1 atmosphere. And we have to do that because the vapor pressure is lowered in a solution. Let's take a look at that. Okay, so we have our picture here again, and we know that this is the pure substance over here, and we know that this is the solution over here, the mixture. Alright, now The vapor pressure on the pure substance is going to reach 1 atmosphere a lot more quickly than the vapor pressure on the solution, because we're able to produce more molecules of vapor. That means we're going to be able to reach 1 atmosphere over here a lot more quickly, and that means that this will boil more quickly and at a lower temperature. Now over here, since we're not producing 1 atmosphere worth of vapor pressure very much, we're going to have to heat it for a lot longer. So let's see. Down here we can put some flames. Yes, those are the best looking flames ever, I know. Alright, and we'll get up to this 1 atmosphere pressure for the vapor pressure, and that's going to equal the 1 atmosphere of atmospheric pressure. And when those two things are equal, then the water or the pure substance will boil. Now over here on this side, we'll put in our flames, and when we do this, we're going to heat it up, and that means that that will become a gas, that'll become a gas, that'll become a gas, and then once it does that, the next molecules of water that are underneath it, they will, move up 1 spot, and they'll be at the top layer, and then they will vaporize and become a gas. And so they're going to have to do that like 3 at a time, whereas this one is doing it, like 7 at a time. So that means that we're going to have to heat this solution over here for a lot longer to try and reach the 1 atmosphere vapor pressure, so that it will equal 1 atmosphere of atmospheric pressure and get this solution to boil. So that means that the temperature is going to increase. If we're heating it for a longer period of time, that means the temperature is going to go up, which means that the boiling point is going to increase. So let's write that. The boiling point will increase or elevate. We can actually calculate what the boiling point of a solution will be in relation to the boiling point of the pure substance. So for example, I know water boils at 100 degrees Celsius. I could calculate what the boiling point of a solution of salt water would be. And we would use this equation right here to do it. So the first part here, this is the change in the boiling point temperature. Then we have I, which is called the Van 't Hoff factor, and that is the number of particles into which the substance will dissociate. Then we have the Kb here, which is the molal boiling point constant, and every substance has its own molal boiling point constant. Water's is this one right here, 0.515 degrees Celsius per molal. And then we have M, the molal concentration of the solution. Now the Van 't Hoff factor actually holds significant importance in this equation because it can sway the boiling point temperature difference by a lot or by a little bit, depending upon how many particles dissociate in the solution. Remember, every time that we have a solution dissociate, we are squeezing more and more solute particles in between the solvent particles. So for example, if you have sodium chloride versus calcium chloride, when sodium chloride dissociates, it's going to break down into sodium ions and chlorine ions. So we're going to get 2 moles of ions out of that one. But when the calcium chloride breaks down, we're going to get calcium ions, and then we're going to get 2 moles of the chloride ions. That means altogether we get 3 moles of ions in this salt. So when I dump this salt into water, it's going to dissociate into more particles than this salt will dissociate into. That means the solvent particles are going to have more space in between them, which means you're going to have to heat the solution up even more in order to get those solvent particles to vaporize and equal the atmospheric pressure and therefore boil. So that means that the boiling point is going to be higher for this solution than it would be for this solution. Okay, so for substances that do not dissociate in water, meaning the organic ones or the covalent molecules, they will have a Van Hoff factor of 1. Okay, so all non-electrolytes or pure substances will have a Van Hoff factor of 1. Remember, non-electrolytes are these things that don't break down. For substances that do dissociate in water, if you have two ion particles form, then you're going to have a Van Hoff factor of 2. So we just talked about how NaCl would break down into sodium ions and chlorine ions, so the Van Hoff factor is 2 here. And the calcium chloride that I had talked about, as I show down here in this box, we have 1 here and 2 moles here, so we have a Van Hoff factor of 3. Okay? You're going to need to know your solubility rules so that you can write the net ionic equations of a particular solution, so that you can figure out how many ions it's going to break down into, so that you'll know what your Van Hoff factor is. Alright, so let's do an example question using our new formula. So it says calculate the boiling point of a solution containing 64.8 grams of sucrose, remember that's a sugar, table sugar, dissolved in 400 grams of water. So the first thing we need to do is write down our equation for the change in the boiling point. Okay, and now we need to decide what things we know and what things we don't know. Alright, they've given us the mass of the sucrose and the mass of the water, and we know that the sugar here is being dissolved into the water. So this is the solute and this is the solvent. I see that we have molal as one of the variables here, and they've given me enough information to solve for the molality of the solution. I also know that my solvent here is water, and I know the Kb of water. We were told that right here. I need to find out what the Van Hoff factor is by writing the net ionic equation, and then I'll be able to solve for the change in the boiling point. Now understand, that's not really what they asked for. They asked for what the new boiling point would be. Remember, when you find the change in something, you're actually finding the final minus the initial. Okay? So we want to know what the final boiling point is. If we find out what the change is, then we can figure the final boiling point out. So let's solve for the molality first. Okay, so now we found the molality of the solution, which is right down here. So we have this variable figured out, we have this variable figured out, and now we need to know what the Van Hoff factor is. So in order to do that, we need to write the dissolution equation, or the net ionic equation, of sucrose dissolving in water. So let's do that. Okay, so here is the net ionic equation for sucrose dissolving in water. We have solid sugar crystals here dissolving in liquid water, and then we get aqueous sugar over here. Notice it does not disassociate because this is a weak electrolyte, so we get 1 mole of particles, which means we have a Van Hoff factor of 1. Okay, so let's go plug all of our information in and find the change in boiling point. Alright, so here we have all of our information plugged in, and now we're going to go ahead and do the multiplication, and we should end up with degrees Celsius as our unit because we have molal on the top and molal on the bottom. So that leaves us with degrees Celsius as the unit here. Alright, and so here we have the boiling point difference between the final and the initial. So we want to know what the new boiling point is going to be, in other words, the final boiling point of the solution. So we need to change this into final minus initial so that we can figure out how we need to resolve that. Alright, so final minus initial is equal to the change. We want to know what the final is. That means we need to add the original boiling point to both sides. Okay, so we add those two together and we end up with the final temperature, the final boiling point, as 100.2 blah 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 degrees Celsius. Now, the givens up here, the least number of sig figs is 1, but we're doing addition subtraction here. We're supposed to end with the decimal points from the given that has the least number of decimal points. This one ends in the ones place, so we really should end this at 100, which would really show that there's no difference at all significantly. But in order for us to actually have a different answer for our problem, we're going to go ahead and cut this off at like 100.2 degrees Celsius. Alright, let's look at the last colligative property. This is going to be freezing point depression. So, as a solution cools down, the particles that make it up are going to start to move closer together. This is all going back to our kinetic molecular theory. But now these particles have solute between them, so they can't get as close to each other as they used to. So that means you have to remove more energy from the system to get them close enough to be able to actually form a solid and freeze. Okay, so let's say that we want this substance to freeze. This is salt water here, okay? Well, these water molecules have these little sodium ions in between them. Now, in order for something to freeze, it has to become a solid. That means that these water molecules need to get close enough to each other so that their cohesive forces are strong enough to stay attracted and make them become a solid. Well, in order to get these water molecules closer to each other, I have to drop the temperature. I have to bring the temperature down. But they've got these little sodium ions in there that's going to make it difficult to get them close enough to each other so that their cohesive forces take over and make them become a solid. So I have to drop the temperature far more than I normally would if I had a pure substance. If I had a pure substance, I don't have to remove very much energy to get those water molecules close enough to each other and sitting still enough so that they form a solid. But this one, I'll have to drop the temperature a lot to make these water molecules squeeze close enough together, and they will be trapping the sodium ion between them, but they'll be squeezing on it, and they'll get close enough that they can actually form a solid. So if the temperature drops that much, then that means that the freezing point is going to have to drop as well. The freezing point will be lowered. So you have to get this solution much colder than 0 degrees Celsius in order to get it to freeze. That's the idea of salting the streets in wintertime. The people will go out and they will pour salt out on their driveways and on the roads and stuff because that makes the solution have to drop way below 0 in order for it to freeze. And so hopefully if the temperature outside doesn't get so far below 0, then the roads in your driveway won't freeze and you'll still be able to drive on them. And the more ions that you can pack in between these water molecules, the better. So like if I did NaCl, then I've got 2 ions. But what if I did CaCl2? Then I get 3. I get 1 calcium ion and I get 2 chlorine ions that I could pack in between these water molecules. That would drop the freezing point even more. Alright, we can calculate the freezing point of a solution with this equation here. We've got the change in the freezing point is equal to the Van 't Hoff factor times the molal freezing point times the molality. So the molal freezing point for water is 1.853 degrees Celsius per molal. Alright, so let's work a practice question. You dissolve 1.2 grams of sulfur in 15 grams of naphthalene. And here's the formula for naphthalene. If the freezing point depression constant, or Kf, is 6.9 degrees Celsius per molal, and the normal freezing point is 80.6 degrees Celsius, what is the new freezing point of the naphthalene solution? Okay, so since they're asking for the new freezing point, that means they want the final freezing point. Remember, change is equal to final minus initial. Okay, so they give me the normal freezing point of naphthalene, so this is the initial freezing point. They've given me the grams of sulfur, and they're telling me that I'm dissolving the sulfur into the naphthalene. So that means this is the solute, and this is the solvent. So I have enough information to get moles of my solute and kilograms of solvent. That gives me my molality. They gave me the Kf here, and I think that we can solve for the Van 't Hoff factor by writing our net ionic equation for that. Let's solve for the molality first. Alright, so here is the molality of the naphthalene solution. We've got moles of solute, kilograms of solvent, we've plugged into our equation, and here we have our molality. Now we need to figure out what the Van't Hoff factor is. Okay, so when we write the equation for the dissociation of sulfur in naphthalene, we see that it doesn't dissociate. Sulfur is a pure substance, okay? It's an element. So that means that we're just going to get 1 mole of particles. That means that we have a Van't Hoff factor of 1. Okay, so we know the molality, we know the Kf, and we know the Van't Hoff factor. We can now find the change in freezing point. Okay, so here we've plugged in our information. We've got molal on top and molal on bottom, so those cancel, and we're going to have degrees as the unit for the change in temperature, so that makes sense. Let's go ahead and do the math and see what we get. Okay, so we get a temperature change of around 17 degrees. Now, we need to find out what the new freezing point is going to be. There is one thing missing from this change in temperature, though. We know that the freezing point is lowered when we have a solution. We have freezing point depression. So this change in temperature here is a negative change in temperature. So let's go ahead and add that in. Now, in order to solve for the final temperature, we just need to use our equation here. Remember, the change in temperature is equal to final minus initial. So that means we need to add the initial temperature, which is the 80.6 degrees Celsius, to both sides in order to find out our final temperature. Okay, so we take our initial, we add it to our change, and here is the final temperature. Notice that it is less than the original because we had freezing point depression here. So since we're doing an addition-subtraction, that means that the sig figs are based off of the decimal places. This one ends in the tenths place, so we need to finish this one off in the tenths place. That would be here where the 3 is, however the 8 is going to round the 3 up. So we end up with a new freezing point of 63.4 degrees Celsius as our answer.